Hello. I'm sorry I cannot be there with you today, or if you're fourth period, that we just decided that we weren't going to do anything. And your lessons we have seen that here. Unfortunately, we can't just today. We're going to have to talk about this material. So we're going to talk about expected values. Now, a lot of you have been taught expected values before, you didn't really know it, but anytime that you take your test average, for example, and multiply it by 30% of tests with 30% of no grade, and then add it to whatever your average is on quizzes and all those kind of things where you're multiplying things by how much they weigh in a percentage, you're taking the expected value. You just didn't know that. So we're going to kind of come in and we're going to actually talk about it and what it means and how to do it and things like that. So expected value, what you do is you would take every outcome, and I'll explain what that means in a second, and multiply it by the probability of it happening. Once you have all those things multiplied together, you will add however many outcomes that you had. So for this first example, it says what is the expected value of a six-sided number cube with sides labeled 1 through 6? So we have 6 outcomes. You roll this cube and you can either relate on a 1, a 2, a 3, a 4, a 5, or 6. So those are what I mean by outcomes. How many results could I get by whatever I'm doing? Because it doesn't give us a specific probability, we have to think, okay, well, then it's just 1/6. You have 1/6 chance of rolling a 1, 1/6 chance of rolling a 2, so on and so forth. So you'll see in the table right in here, okay, that it's got each outcome. So you can roll a 1, you can roll a 2, you can roll a 3, 4, 5, or 6. So it listed the outcomes that could happen. The probability of each of these outcomes is 1/6. Okay. Now this would depend on how many times it occurs. Let's say that I had a dice that dice are normally 6-sided that only has numbers 1 through 4. Let's say 2 repeated and 3 repeated. Well, 2 no longer has a probability of 1/6. It shows up on 2 out of the 6 sides, so that probability would be 2/6. So it's a little bit, it's kind of easy when we're talking about spinners or dice or things like that. For the most part, the probability is going to be 1 out of however many sections you have. So if I wanted to find the expected value, okay, of rolling any specific number, we would take the probabilities. So you would see we've got outcomes listed here. We can roll a 1, a 2, a 3, a 4, a 5, or a 6. So the outcomes are listed. And next to the outcomes being multiplied together are the probabilities. So you can see that every outcome is being multiplied by the probability of that outcome happening. This is really easy if you make the table, because you're pretty much just multiply, 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 multiply. Then adding each thing together. So making the table is going to make it a little bit easier on you. I'm not going to make a table for everything in these notes, but making a table is probably going to be a little bit easier for you. Well, 1 times 1/6 is 1/6. You see it here. And 2 times 1/6 is 2/6. And notice I'm not reducing these because I have to add them all together. You've got the same denominator already. All of these denominators are 6. If I were to start reducing, like 2/6 is actually 1/3, then I've got to work on getting it back to common denominators, and that just doesn't make sense. So I'm not reducing here. I'm just going to go ahead and add everything together. 1 plus 2 plus 3 plus 4 plus 5 plus 6 is 21. So you see here, we've got 21/6. 21/6 is 3/5. Or 3.5, I apologize. So the expected value of rolling any specific number on this dice is 3.5. So let's kind of see what I'm talking about. I was explaining to you a little bit earlier that if, let's say, the dice had multiple numbers or a number on multiple sides, what would we do? Well, in this case, okay, we've got, and this doesn't look like a dice, a cube, And it's kind of got the cube folded out so you can see what's happening on every side of the cube. So we've got a side that's got a 1, we've got 2 sides that have a 2, 2 that have a 3, and then the last side has a 5. So for this, I am going to go ahead and build my table. My top row is going to have the outcomes that could happen. Okay, so what outcomes could happen? What number could I land on by rolling this cube? I can land on a 1, I can land on a 2, a 3, or a 5. Apparently somebody didn't like 4, and so it's not included in the cube. The next row is going to be the probability of those. So I only have one side labeled 1. Okay, 1 out of the 6 sides. So the probability of rolling a 1 is 1/6. I've got, let's do it in another color, 2 sides that come out as a 2. So the probability of rolling a 2 here would be 2/6. Same thing with 3. Got 1 3 here, another 3 here. So 2 out of the 6 sides have a 3. And then finally, I only have 1 5. So 1 out of the 6 sides is 5. So the probability would be 1/6. So you're literally just recording how many times you see this outcome. Okay, how many times does this happen? Now we're going to come in, multiply the columns. I have 1 times 1/6. The outcome of 1 can happen 1/6 of the time. The outcome of 2 can happen 2/6 of the time. The outcome of 3 can also happen 2/6 of the time. And the outcome of 5 can happen 1/6 of the time. So I'm going to come in, I'm going to multiply these things together and then add everything. 1 times 1/6 is 2/6. 2 times 2/6. Think about 2 as 2/1, and with fractions we multiply across the top. So the top would have 2 times 2, which is 4, and the bottom would have 1 times 6, which is 6. So 2 times 2/6 is 4/6. Same thing, 3 is really 3/1, so up top I would have 3 times 2, which is 6, and underneath I would have 1 times 6, which is also 6. Then finally, 5/1 times 1/6. 5 times 1 is 5. 1 times 6 is 6. I'm going to just add across the top. We already have common denominators, so I'm not really worried about getting common denominators. I can just add across the top, and I know that my denominator will stay 6. 1 plus 4 is 5. There's another 5, so that's 10. And then a 6, that's 16. Well, 16/6. Get calculator going. 16, maybe. So that's not going to work. Hang on one second, okay? All right, back, sorry. This comes out as 2.6 repeating, so it's 2.7 if you round it. So we have the expected, we can expect to hit each one 2.7% of the time. So when we start working on application with these, meaning word problems, where is this going to show up in roulette? Most of us are not going to be just rolling random 6-sided dice all the time and trying to figure out the expected value. A great place is when you're talking about traffic and what is the best route to take for games and things like that. Is this a fair game? This is, any of you who have seen 21, when you count cards, you are working with expected value. It's based on what cards are left in the stack if you have already gotten some of these other cards. So you can put this into a lot of different places, but a lot of the things that we're going to work with today as far as examples deal with traffic or taking routes and things like that. So Lisa has 2 choices of routes when she goes to school. Route A always takes 15 minutes. Route B takes 12 minutes, unless there's a traffic jam, in which case that route will take 20 minutes. The chance of a traffic jam is 15%, which route should she take? So you see here that we've got that route A is always 15 minutes. There's nothing that changes that. Somehow she has found a route that never, ever, ever will get traffic, that she can always make it in 15 minutes. Whereas route B, you'll see that we've got a little bit more information here. So let's talk about this one first. Okay. We get this 20 times 0.15 from this right here. Okay. The 20 meaning 20 minutes because the outcome is that it would take 20 minutes. And the 0.15 is the probability. It says that you only do the 20-minute route if there's a chance that a traffic jam would happen 15% of the time. Okay, so that 15% is based on this 20-minute route. So the outcome of 20 happens 15% of the time. We don't actually plug in percentages, we plug in decimals, so 15% would be 0.15. Well, if 15% of the time there's a traffic jam, what percent of the time is there not a traffic jam? 85%. So that route will take only 12 minutes, meaning there's no traffic jam, 85% of the time. So if you wanted to make your table, the outcome of 20 minutes, the outcome of 12 minutes, well, 20 minutes represents there being a traffic jam. It said that happened 15% of the time. There's 100%, which means if something happened 15% of the time, the other thing happened 85% of the time. So that's where those numbers are coming from if you wanted to make the chart. Which route should Lisa take based on this information? Should she take route A, which always takes 15 minutes? Or should she take route B, which she can expect to take about 13.2 minutes? Most of the time it's going to be closer to 12, but some of the time it's going to be 20. So you kind of almost think of this as an average. You should be saying that she should take route B, okay? Because even though route A is consistently 15 minutes, and route B could potentially take up to 20 minutes if there's a traffic jam, most of the time there's not a traffic jam on route B, and most of the time she's going to be able to make it in about 12 minutes. So that's going to be a better shot. It's not really a shot in the dark. Now for us to try to figure out what route we should take to work or what route we should take to school or wherever else you're going, you don't know traffic trends. If you knew traffic trends, you could kind of figure it out. Okay, but you would have to have a little bit more information for you to make this kind of a decision in your real life. So again, otherwise, it's a long one. What I really kind of want to do is I want to just kind of center in on some specific information. So first thing I'm going to do is I'm going to make my table. Again, top row is outcomes. Sorry guys, even when you're an adult, your parents still call and find out what's going on. So let's get back to this. So my top row is still my outcomes, okay? Bottom row is still going to be probability. So when we read this application problem, we're going to be looking for specific things. First thing we're going to be looking at is the different outcomes that we can take, okay? So I'm kind of going through this. I'm not even reading it really. I'm just kind of looking, and I see a couple different things. I see route A, route B, route C. Those are going to be the outcomes because I can probably decide that this is going to ask me which route this person should take. There's 3 options of routes. So we're probably going to have to figure out which route is the best. So I'm going to go ahead and say that there's 3 outcomes and that they match the 3 routes that I've been given. Okay. Now I'm going to go back in and I'm going to look at every route individually and I'm going to see what information there is about it. So I'm going to look at route A first. So route A takes 16 minutes most of the time. And then I see later it says there's a 40% chance that whoever this person is going to encounter an accident on Route A. And if they encounter that accident, it's going to increase their travel time to 20 minutes. So I'm going to start figuring out what is going into probability. It says there's a 40% chance that this person is going to get into traffic. And if they get into traffic, it's going to be 25 minutes. So 25 minutes, 40% is 0.4. Okay. But then if I go back to it, it says normally it takes 16 minutes. So if it takes 16 minutes when there's not a traffic jam, and there's a traffic jam 40% of the time, what percent of the time is there no traffic jam? What percent is it actually going to take 16 minutes? You should be saying 60%, which is going to be 0.6. So I'll come back and we'll actually figure out what that number is later. But let's go ahead and move on to Route B. So I'll erase everything I've got underlined about Route A. Pick a new color. Route B typically takes 10 minutes. Okay. There's a 20% chance that so-and-so will encounter an accident on Route B, which would increase his travel time to 40 minutes. That's a pretty big difference, going from 10 minutes to 40 minutes. So is there traffic jam 20% of the time? What percent of the time is there no traffic jam? We should be saying 80%. So it would take 10 minutes 80% of the time. The other 20%, if he gets caught in a traffic jam, would take 40 minutes. So I've got 40 times 0.2. 10 minutes 80% of the time, and 40 minutes 2% of the time. This hopefully is getting a little easier. You're starting to kind of figure out the order things go in. Last one. Route C typically takes 20 minutes. Sorry. There's a 10% chance of getting into an accident or into traffic, on Route C. And if you get into that traffic, your time is going to go up to 32 minutes. So if there's traffic 10% of the time, what percentage are not traffic? Should be saying 90. So it's going to take 20 minutes 90% of the time. It's going to take 32 minutes. Of course, I need to expand my table because I write too big. It's going to take 32 minutes 10% of the time, so that's 0.1. We're going to find the expected value for each one of these routes, meaning we're going to basically find what we could expect, how long we could expect on average to spend on these routes, okay? So if I have 16 times 0.6 plus 25 times 0.4, I get that this route A should take right around 19.6 minutes a day, kind of on average, taking into account the percentage of time there are accidents and delays. Route B, 10 times 0.8 plus 40 times 0.2 comes out at 16 minutes. Okay, so we could expect to spend about 16 minutes, give or take, on Route B. And then finally, Route C takes 21.1 minutes on average each day. You can expect to spend that amount of time. So what route should, who is this person, Jack, end up taking? You should be saying Route B. It's got the lowest expected value. We can expect to spend the shortest amount of time, even though if there is a traffic jam, we're going to spend way longer than any other route. Traffic jams are only going to happen 20% of the time here. Okay? So we're going to be sitting a little bit closer to that 10-minute mark most of the time. Okay, we might sit next to the 40-minute mark, but for the most part, we're going to be on the shorter time frame. So Route B is going to be the best bet for us. This is another one that's pretty much the exact same thing. In this one, the person is working to climb a specific route to go to a hiker. And whether or not there's ice on the route tells you about how long it's going to take to climb this route. He'd like to climb the one that he can expect to take the lowest amount of time. Take it. Okay, start with my table. So make your table. And you're just going to work on filling it in the same way that we did earlier. Outcomes, probability. For here, we have a southern root. When you read it, you've got a southern root, you've got an eastern root, okay? So we've only got 2 outcomes on this one. Let's concentrate on southern first. So for the southern route, it normally takes 2 hours, okay? But if there's a chance of ice, which is 20% on the southern route, it takes a little bit longer. It would increase him to 4 hours. So if the ice is only going to happen 20% of the time, that means there's no ice 80% of the time. So 80% of the time, it's going to take him 2 hours. There's ice 20% of the time, so 20% of the time it would take him 4 hours. Step over to eastern, okay? It takes him 2.5 hours normally. But if there's ice, that's going to increase to 3 hours. So we just need to fill in the percentages. There's ice 40% of the time on the eastern route, so we've got 3 times 0.4. If there's ice 40% of the time, there's no ice 60% of the time. Again, multiply them together, figure out what you get. Staff, you should be saying that he could expect to spend 2.4 hours hiking the southern trail. Whereas the eastern trail, he would expect to spend 2.7 hours. So if he doesn't want it to take very long, he's going to want to pick that southern trail, okay? Even though 4 hours is more than 3 if there were to be ice, there's only ice 20% of the time. So you can probably expect it's only going to take somewhere around 2.4 hours. Sorry, guys. My phone's going nuts. So one of the things is you specifically can use this, okay, and things like it. We're going to get into probability rules. So what is probability? Is something of multiple things happening. So it depends on if it's and or. Now, I'm going to handle this in a different video since this video is already coming up on 20 minutes long. So make sure you go watch the other video and I'll explain your project in that video as well.